Hello, everyone. This is our quarterly research and development research webinar. My name is Alan Lung, and I'm the Customer End Use Application Technology Development Project Manager on the SoCalGas Research Development and Demonstration, or RD&D team. For today's webinar, we will be welcoming Mr. David Saigon from Gas Technology Institute, or GTI, to discuss his research on the thermal particle fluid for commercial industrial emissions reduction. This project is being supported through the ARPA-E and the CEC. Just as an FYI, today's webinar will be recorded. You can access today's recording as well as our past webinar series on our SoCalGas Research and Development webpage. Before we begin, I'd like to walk everyone through the GoToWebinar toolbar that should be visible to all attendees. Please enter any questions in the questions box. We'll review these during the Q&A session after the presentation. During the Q&A session, we will also open up the discussion for verbal questions. If you'd like to speak, click the raise hand icon to be called on during the Q&A session. When you are called on to ask a question, we will first grant you access to unmute, then you must manually unmute yourself. After asking your question, please go back on mute. Finally, you will find a few valuable documents in the handout box, including today's presentation. Now, a comment on SoCalGas's commitment to diversity. SoCalGas is dedicated to improving the quality of life in the diverse communities we serve. To support this commitment, SoCalGas RD&D staff conduct outreach effort and activities to engage with the disadvantaged and underrepresented groups throughout California. For example, in 2021, RD&D conducted 5 community outreach sessions to facilitate a dialogue with leaders from community-based organizations from across the SoCalGas service territory. Participants include El Concilio Family Services, the Black Voice Foundation, the Asian Youth Center, Community Action Partnership of Kern, UC Riverside, and Cal State LA. Other outreach efforts also include notifying researchers, entrepreneurs, and businesses about RD&D program funding opportunities, share the results from RD&D projects to inform and educate the general public. Today's webinar is just one of the several ways we do this. And lastly, track and report progress in diversity outreach efforts in our annual report. The SoCalGas RD&D program is divided into 5 areas that span the entire energy supply chain, from low carbon resources where they look at the renewable gas production, to gas operations focused on the technology development of the operation side of the gas supply chain, to ultimately where we use the gaseous fuels from the clean transportation, clean generation, and clean customer end use applications. In 2020, the SoCalGas RD&D team managed 386 active research projects. On average, RD&D projects generate a 6.9 funding ratio, meaning for every dollar of RD&D funding provided to a project, the project also received nearly $7 of external co-funding. For example, in 2021, 11 RD&D projects were awarded about $48 million from the CEC and the DOE. More details on the RD&D program are available in the 2020 annual report, which is included in your handouts today. We produced a Spanish version of the annual report to better connect with the diverse communities in our service territory. You can also find this in the handout. I'd like to share with you an upcoming webinar on May 19th. We will hold Bridger Photonics to learn more about their airborne LiDAR for faster leak detection. Finally, we want to stay connected with you, our stakeholders in the research community and the general public. Please visit our webpage where you can find our annual report, news about the RD&D program, and recordings of our webinars, including this one. Please reach out to the RD&D team via email with questions, comments, or research suggestions. We also maintain an RD&D page on LinkedIn and on the CEC's research networking platform, Empower Innovation. Now, without further ado, I want to welcome Dave Saigon from GTI. Dave is a research and development director at GTI, a nonprofit institution serving the gas industry. With over 30 years of experience, Dave oversees the industrial and power group and is focused on keeping the company at the forefront of innovation, providing vision and engineering continuity for all energy applications. He holds both a bachelor's and a master's in metallurgical engineering from the University of Illinois at Chicago. Dave, I'm excited to hear the story behind your research and the technology you're working on that can reduce emissions for commercial and industrial process. And now I will hand over presenter mode to you, Dave, so you can provide us with the details.
Thank you, Alan. Let me just switch to the slide deck. Can you confirm that you see the slides?
Yes, I can see them.
Thank you. Good morning, good afternoon, everyone. A special thank you to the folks at SoCalGas for allowing me the opportunity to present this exciting topic to you today. Today's topic is an innovative approach to use particles to capture heat and transport that heat through various processes within a particular facility. The rebalancing of heat can lead to efficiency gains or product output gains as well. And what I'd like to do is focus initially on a foundation, talking about the industrial sector and the amount of fuel that's consumed, moving over then to thermal heat, and then transitioning from that foundation to an actual discussion of the results of our work, and then close out the talk today with discussion on applications for this particular technology. The U.S. industrial sector is very broad. Across the United States, it consumes approximately 20 quads of energy. And these, shown in the graphic here, these 15 sectors consume overall 95% of that energy, with the top 5 sectors consuming approximately 74% of the energy. This is important because when we look at the industrial sector, it has a tremendous energy appetite. But if we look at the use of the actual energy, we see that basically only 7 quads of energy go to the process itself. And there's approximately 16 quads of energy that are essentially wasted. That energy doesn't participate in the process, and it essentially goes up the flue or the stack, and it gives us an opportunity for waste heat capture. We also look at the industrial sector as being one of the top producers of CO2 emissions. And we certainly don't want that designation. But most of the CO2 emissions in this area are from combustion, and natural gas is the primary fuel source. We can see here on the graphics that there's quite a distribution between the CO2 emitting sources, but overall, greater than 35% of that comes from chemicals in the refining industry, with quite a diverse application as well. When we look at industrial thermal heat, there's 2 paths forward. One is the direct route that could be used in fluid heating application or distillation or drying, such as textile drying. And the other could be direct, where it basically is used to produce steam for the process. And the processes in the industrial space are very, very broad. They range from operation process temperatures from hundreds of degrees all the way up to thousands of degrees. And you see a pretty substantial distribution of the energy portfolio for different processes on the right side of the screen. When we look at the future and we start to have all these discussions about decarbonization in the industrial space, we start to hear about the use of hydrogen, ammonia, other alternative carriers. There's one thing that's for certain about the future, and that's the fact that end users will demand that the thermal energy fulfills their requirement for the process at a competitive cost. We basically see this demand and we characterize it two ways. The first is a temperature, which is set by the process. It could be a roasting application, or it could be a batch furnace, or a typical boiler application, and these vary significantly. The second attribute is set, and it's called the load, and that's the rate of thermal energy that needs to be transferred to accomplish that process. And the underlying fact is that industry needs to have energy that provides the temperature required, and they need energy that's going to provide a substantial load for the process. I found the table on the right side of this graphic very interesting in the fact that most of the facilities can be characterized as from 1 to 10 megawatt in capacity. And this is going to be an interesting dynamic that I touch on and later in my presentation as well. When we look at effective thermal energy management, the best way to utilize energy is for every BTU that's consumed, that BTU needs to play an active role in the process. We're simply not at that level right now. There's been significant discussions about waste heat characterization across different sectors. And this most recent study characterized the spectrum as low-grade heat is below 300 degrees, and it's about 22% of the market. The mid-grade from 300 to 450 degrees Fahrenheit is about 25% of the market, and greater than 450 degrees Fahrenheit is over half the market. And when we look at this, we ask ourselves, okay, there's significant opportunity to recoup BTUs here and apply them to different processes within that application. And essentially, if we want to really make headway in terms of moving towards a decarbonization approach globally and as well in the United States, we need to start looking at energy management. It's easy to say that we can switch to electricity or hydrogen or whatever the alternative carrier fuel would be. But remember back that I mentioned that the industrial sector consumes almost 20 quads of energy, and that a good portion of that, about 14 quads of energy, does not participate in the process itself, and it's essentially wasted. So it's going to be one thing to try and find alternative sources for 7 quads of energy, and it's going to be much more difficult to find alternative sources for that full 20 quads of energy. What I'd like to do here as I transition over to the actual project activities itself, I'd like to pause and mention that these sponsors, Southern California Gas Company, the Energy Commission, and an outfit called Utilization Technology Development, which is a consortium of gas industry members, all participated in funding the work that I'm talking about today. They all participated in the ARPA-E solicitation. And those that are not familiar with ARPA-E, it's a branch of the Department of Energy, the Advanced Research Project Agency for Energy. It's a very high risk, high reward type of organization where they'll give you significant funding to look at a cutting edge technology that has large market impact, and it's milestone based driven. So you set up your milestones, you work towards technical performance, and if you don't achieve technical performance, then your funding is basically cut. So our team is actually in our 3rd award with ARPA-E. it's really unprecedented because most awards only last a single award and they go through the process and they move on. But we've made significant strides with achieving a cutting edge technology that I'll talk about today. And I even had the honor of presenting for ARPA-E at a congressional workshop. Our team was one of 7 teams that were selected to present in front of this congressional workshop. And we had a poster presentation that talked about our results and our progress. And from the research perspective, I would have never thought that I would be presenting at that level. It was truly an honor and probably the most fulfilling day of my career. As we look to the development team, there's some pretty big names here. The University of California at Merced, Dr. Roland Winston is the founding father of non-imaging optics that we included in the solar development work. The Particulate Solid Research Institute, it's a not-for-profit organization that focuses on particle handling and transport of materials. And it's basically a wealth of information, how to convey materials. Stanley Consultants is a worldwide consulting firm that's basically putting together a front-end engineering analysis for the program so that early adopters of the technology will have specifications to look at in terms of design and build. And USG, right there in Southern California, has an eye towards sustainability and is an early adopter working with us to make inroads for the technology. They're focused on the environment and a start to the community in terms of sustainability, energy efficiency, water recovery, and so forth. I'll pause on this slide and give you the opportunity to read as I speak through the topic. But when ARPA-E first started the solicitation, we responded to a call to increase the temperature output from a typical parabolic trough. And for those who may not know what a parabolic trough is, it's a large mirror that's curved and it has a pipe that goes across the front of that mirror through which a thermal fluid travels to capture the heat from the sun. And these parabolic troughs essentially are quite large in their footprint. And they're typically like 2 miles by 3 miles in footprint. And the temperature output from a typical parabolic trough would be about 400 degrees C. And what ARPA-E was looking for was innovative technology that would increase the output temperature from that parabolic trough. We would essentially then be able to reduce the footprint and have a smaller operation, or if we kept the same footprint, we would be able to have a higher temperature output. And so what we selected, we presented to basically present a non-imaging optic design that had a novel heat transfer fluid, because now as we increase the temperature output from the parabolic trough, conventionally available heat transfer fluids no longer exist. Certainly, you could go to 565 degrees C like they do at a tower operation with molten salt, but our goal was to achieve 650 degrees C. And so early on with the process, I was always very vocal with ARPA-E that really the end game was initially to design the system for a 100 megawatt solar farm. And I was always advocating that on an annual basis, how many of these solar farms are really built? I would take a step back and I would say, let's look at the industrial process heat market. There's a lot of industrial users out there that are really struggling in the summertime with their cooling loads. They may have like a 6 megawatt combined heat and power system, but once they're in the summer and the cooling load comes on, they're at capacity. So they would very much welcome the opportunity for additional process heat, and especially using a renewable asset like the sun. So we kept at that, And slowly, as we've gone through the 3 awards with ARPA-E, they're very receptive to the first entry point being in the process heating market. And so as we develop the technology and scale it up, we see the first market entry point as being a 2 megawatt system. And what we envision from this is through the process, we envision at least capturing 40% of the solar energy or 40% of the industrial heat energy and being able to transport that through the system. So let me show you graphically how the system works. If we were to have a sun shining down on a typical parabolic trough, which is a curved mirror with a pipe in front of it through which the heat transfer fluid travels, that sun would shine onto the mirror and the rays would heat up that pipe. Now this system on sun could easily be replaced with a batch furnace or a galvanizing line or a reheat furnace or a roasting operation where instead of the pipe receiving the heat from the sun, this pipe would be located in the flue of the process, and the flue gases would travel across this pipe to heat up the fluid. And so the way the process works is that there's a hopper over here full of particles, and there's a blower. And the blower starts and it conveys particles through the piping, through the heat source. The heat is conveyed from the process into the particles, and then the particles are then transferred to a storage hopper for storage at a later use, or it could be directly transferred to the process itself and go through a heat exchanger to dissipate the heat that's collected to the process. And then as the particles leave, they cool down and return back to the storage vessel, a closed loop system. So when we look at it from the solar perspective, we have this solar concentrator, the parabolic trough, and the gray cylindrical pipe there is the typical absorber. What our process does is it adds a vacuum tube around the gray pipe or the absorber, and that's a vacuum. And inside this glass pipe, there's this red image that represents a secondary concentrator. And so in the traditional sense, when the sun comes in and is reflected off the mirror and absorbed onto the heat, onto that absorber there, only a very small section of that absorber is illuminated by the sun. But by adding these non-imaging secondary optics shown in red, we are now able to take the solar coming in and bouncing off the mirror, and it bounces off the secondary absorber to completely illuminate the absorber. We call this the pi effect. And so that allows us to take what would be a traditional receiver that operates at a temperature output of about 400 degrees C and increase the output temperature up to 650 degrees. Not a lot of changes, just very specific changes. And so when you look at the industrial heat aspect of it, you can step back and say, well, what if I don't want to do solar? I have this nice reheat furnace that has a lot of heat going up the stack. Let me replace the parabolic concentrator with an industrial application, my reheat furnace, and I'm able to grab that energy going up the flue and then recycle it back to the process or another process within the plant. There's tremendous opportunity there for advancement. When we look at the industrial sector, over 46% is dedicated to process heating applications. A lot of potential moving forward. And so let's talk about the fluid. We have this particle, and we convey the particle through the system with compressed air. Very generic, nothing elaborate. And when we first started out the research activity, we looked at about a dozen different particles. Some of them stick, some of them clog, they didn't work. We looked at different size particles. We really started to dig in and found the limitations of different sizes. And it's important to have a certain shape of the particle, because as the particle is flowing through the system, you certainly don't want abrasion of that particle destroying your piping and so forth. And so we spent a lot of time characterizing the particle flow as well. And we use something that's called dilute phase transport. And what I would equate that to is like being in the middle of a snowstorm with the particles being the snow coming down. And then ultimately what we did is we focused on something called dense phase transport. And I would equate that to having a tube of toothpaste and squeezing on the end of the tube, and the particles travel through the piping in a slug fashion and just travel through the entire network as that slug moving forward. So we learned a lot during the development, and it was really exciting. And to compare it to what's in the typical parabolic trough, they use something called therminal, which is $53 a kilowatt hour. And it needs to operate at 170 pounds of pressure. And it has a tendency, if it's exposed to air, it's flammable and it could catch fire. Our particle systems operate at low pressure, 25 pounds of pressure. They're non-corrosive, they're non-flammable, they're very stable. And in an upset condition, if we were to lose compressed air, for example, the particles would just fall out to the bottom of the pipe. We would be able to restart the system and move on. So in terms of high temperature heat recovery, there's two paths. The first is to have a solar concentrator and have the benefit of capturing solar heat for the advancement. The second path would be to apply that technology through an industrial heat application with proper particle handling equipment, which is all very mature, and it would transport the particles in a dense phase mode, and it would offer the storage component as well. This particular graphic shows a little bit more details for those who may be interested. In a typical charging operation, you would have the particles leave the cold hopper at, say, a low temperature. They go through the solar component or the batch furnace in the industrial sense, pick up that heat and come back. And then in the discharge, you would essentially send the hot particles through a heat exchanger. And what's critical here is that you have the ability to store high temperature process heat for off-design time throughout the day. In order for solar to really be a viable technology moving forward, it needs a storage component mechanism to it, and this offers that mechanism. On this particular slide, it shows some of the early work that we've done at the University of California, Merced. And it shows the particle rig in the background on the left graphic, together with a parabolic mirror and our absorber that was 1 meter long on sun testing, and a close-up of that image on the right side. It's really impressive to see the amount of sun coming off the mirror and illuminating that 1 meter long absorber. This particular system has operated at 685 degrees C. That's the outlet temperature. That's over 1200 degrees Fahrenheit. And we had multiple discharge cycles that we had throughout the test campaign. And what I mean by that is the storage hopper has a defined volume. And as you go through and transport those particles through the system, you would come to the point where you consume the available volume of particles in that storage vessel. And then you have to go ahead and recharge the system for the next round. We consider that a particle cycle. And we have over 200 cycles on this particular system on sun, producing heat at 685 degrees. Very impressive. There's no one in the world that has even come close to this. We heard a couple months back about an initiative with Bill Gates where they achieved 1,000 degrees C, but it was not sustained over a long duration. And a trough, a power tower like they have operating, operates at only 565 degrees C. So this is cutting edge, world-class technology that what we're hoping to do is apply it to the industrial space in the process heating area. And so we started that work with the smaller 1 meter long absorber. And now we're in the process of transitioning that work to a typical parabolic trough. And for those who may not be knowledgeable in that area, there's an image in the lower right-hand corner here. A parabolic trough is 17 meters long by 7 meters across. And the solar farm is made up of several of these. And when we look at scaling our technology, we would need about 90 of these parabolic troughs to have a 2 megawatt system. And so right now we have a parabolic trough, a single unit installed at the University of California, Merced, where we're conducting a test with the absorber to basically characterize the performance of the system. The work that's been completed at GTI has been the particle work. And we built 2 test rigs that will be transported out to University of California, Merced, and then combined with the system, and the entire unit will be tested on sun. Really excited about the potential to bring these 2 units together. And this particular slide shows the particle work that we've tested and developed at GTI. On the left side, you see a storage hopper. And just kind of give you some perspective, this is 6 foot by 6 foot, and it's about 16 feet tall. And it's all skid mounted, ready for transport. It can be turned on its side and transported via semi-truck from outside of Chicago, Illinois, to the Merced campus. And these smaller pictures show how we've integrated all the controls onto the skid to make it self-contained. And as we transport the particles through the system, we use this load cell on the storage hopper to give us an idea where the particles are. We know what the initial weight is of the storage hopper, and we know how much weight we put in the hopper regarding the particles. And as we monitor that weight in this vessel, we also know the length of the piping that connects these 2 units and the diameter, so we could characterize where our particles are throughout the system. And then on the right side, you see the other 2 units that we built, called the receiving hopper up at the top and the lock hopper at the bottom. So if you recall the schematic that I showed you earlier, the way the system starts is that compressed air would start flowing through a pipe here that would be located at the bottom. The particles would drop into that pipe, and somewhere magically between these 2 pictures is your heat source, whether it be a parabolic trough or whether it be an industrial type batch furnace or roasting operation. The particles travel through that heat source, and basically end back up into the receiving hopper at the top. And through a series of opening the valves, we're able to transport the particles to the lower hopper, and then through a series of piping back to the storage hopper and complete the cycle. And each cycle is a complete use of the particles available in that particular hopper. So let's talk a little bit about the advantages. This is really what is a necessity for solar to be available mainstream. A dispatchable, renewable storage solution where solar heat can be captured, stored, and then used at a later date. We're very inclined to the sustainability movement, the synergies with the environment, the environmental awareness and safeguards as we're developing the technology to ultimately expand the renewable portfolio. And I'll show you in the next slide a little bit more on the solar. But the main driver here is the potential to come away with solar heat or industrial process heat by reducing the consumption of fossil fuels and CO2 emissions. So we're contributing to our future in a sustainable sense, being able to manage the fuels that we have and the mix of technology that we have. And what I've shown you today essentially uses, for the most part, mature technology, with the exception of the non-imaging optics that were part of the solar collector. And it offers a tremendous opportunity to capture some of that waste heat that's available in industry. So this particular graphic shows the temperature spectrum that we've tested. And I apologize, it's in centigrade, but the horizontal axis is particle temperature in degrees C and thermal efficiency. And it shows the data points as we ramp up the system. And I like to show this plot because earlier on, when I talked to a variety of people, they would always comment that, well, we're not interested in those high temperature applications. 650 degrees C, 1200 degrees Fahrenheit, it's way above where we are. And so I deliberately mapped the system as we went up in temperature. And if we go back and remember that waste heat report that I mentioned earlier that talked about 22% of waste heat being available below 300 degrees F. So 300 degrees F is about 150 degrees C. So if I draw an imaginary line right here, everything to the left of it falls in that low temperature heat regime, whereas there's about 22% available. And if we take that up to the 300 degrees to 450 degrees F, that would be roughly 150 degrees to about 230 degrees C. And so that's that middle temperature regime that's right in this area here. And then once we go above 450 degrees F or above 230 degrees C, that's everything else. So we can easily apply this technology to about 75% of the waste heat that's available across the industrial market today. That's really a game-changing technology because it's easy to apply a technology to the higher temperature applications, but as you start going to lower temperature applications, it gets much more difficult. And so in terms of applications, we see process heat as the near term. It can certainly be power generation, but that's complicated by the power block, and there's significant additional costs associated with the power block. So I would prefer to defer that for further down once we get some experience of putting these units in the system out into the application and end user environment. And the other point that I wanted to touch on is that based upon my industrial experience, there's a lot of end users that are really limited in terms of capacity with their existing system. They're peaked out in the summertime because of the cooling loads, the electric infrastructure, with the blackouts that are rolling across the state periodically. But there's also those consumers that are at the limit of their permit. They cannot burn any more additional fossil fuel because they would go over the permit value. So this type of technology gives those users the opportunity to back off on fossil fuel, to basically increase their production output by installing such a system as this. And it would allow end users to be able to move towards a decarbonized environment and also allow fuel switching. So in terms of the power, solar power spectrum, this graphic at the right shows essentially where we're at. We're all the way out at the end. We're past anything that's commercially available in terms of heat generation right now at the 685 degrees C that we've already demonstrated in the system. And when we look at the lower temperature spectrum, you know, the parabolic troughs have a long range that would be able to help industry. Unfortunately, a tower application would not be suitable for industrial application. But if we take the solar component away and just look at industrial heat, you know, the graphic shown here based upon energy data from the annual energy outlook, the blue bars are natural gas and the yellow bars are electricity, with the green bars being renewables. And the top line is based upon 2019 data, the latest at the time. And then the second line is based upon data for 2050. There's really a lot of emphasis here for these bars to be kind of shifting, going smaller possibly on the blue, the green bars expanding a little bit as more renewables come into the spectrum as we move out and move through the system towards commercialization. The biggest market and the largest potential is in the process heat. I started out my presentation by talking about the waste heat being a significant source, about 14 quads of energy. And these top 5 sectors are mainstay in the state of California. I mean, the vast majority of food is produced in the San Joaquin Valley. And, you know, there's just a tremendous opportunity there to capture the waste heat that I've talked about earlier. So in summary, we hear a lot about decarbonization. It's really starting to gain momentum globally, as well in the United States. And as a research engineer, I really have a lot of questions. I don't necessarily have all the answers, but in terms of decarbonizing, there's certainly a path moving towards hydrogen or ammonia or other alternative carriers. But I prefer to take that step back and reflect on the situation that there's a significant opportunity in terms of energy load that we need to do some, for lack of a better word, housekeeping on. We need to be better in terms of how we use our BTUs and apply the BTUs to the process. A technology such as this offers significant potential for improvement, as well as emission reduction through the reduction of fossil fuel and CO2 emissions. And on the same side, it would make natural gas even more competitive. Tying it together to augment the load and provide solutions for end users is really critical moving forward. And it also offers an opportunity for low loss transfer of heat, as well as storage of heat for use at off-design conditions. You can generate a lot of heat through those particles, storing them in that vessel at higher temperatures that can then be employed through your process. And these different flow devices at high temperature using this type of media could be applied to practically any type of furnace or application. You can see the piping go through the flue work of a boiler, for example, or a batch furnace or a roasting operation. It doesn't matter whether the process is batch, continuous, or cyclical. It's heat, and we're capturing that heat and we're moving that heat towards an area that would have active utilization of that heat. So in closing, I really thank you for your time and attention today and the opportunity to present. You see there on the slide my contact information. By all means, reach out to me. I'd love to have a conversation with those that see an opportunity to move the technology forward. And as we get through the next gate, I'm hopeful that Southern California Gas Company will give me another opportunity to possibly talk about the first installation as we move forward. I think that the technology is really a game changer, and I hope you found this presentation as interesting as I find the topic. Thank you for your time.
Thanks, Dave. That was a very informative and exciting presentation. Now I'd like to open the webinar up for about 10 to 15 minutes for Q&A session. A quick reminder for our Q&A, if you have a question, click the raise hand icon and we will call on you to grant you access to unmute. Then you must manually unmute yourself to ask your question. After asking your question, please go back on mute. If you'd like to ask your question in writing, please feel free to use the question box and we will ask the question for you. I will now go ahead and read the questions, and including the name of the participant and the comments. Feel free to raise your hand and I'll also select you as well. So I did receive a question from Kevin Best. His question was, a 20 megawatt electrolyzer produces about 10 megawatts of low grade heat. Can you imagine recovering this 24/7 and delivering renewable steam for 24/7, say for drying biomass?
Yeah, I mean, certainly I'd love to be at that scale right now. That's just a great example for a long-term vision that as we move the technology forward, look at all that heat that could be utilized and repurposed and redirected. That's a significant amount of heat. Unfortunately, we're still at the lower end of the spectrum. You know, we're trying to get to that point where we're proving the technology on a furnace itself or on a single parabolic trough. Once we're successful there, then it's moving up to a 2 megawatt system. And then, you know, the next logical step would be, you know, something of that nature. But the 10 megawatt, wow, that's a lot of great opportunity there. Gives me hope for the future.
Thank you, Dave. I see that a Phil Suk Kim is raising his hand. I'm going to go ahead and unmute that person. Go ahead and speak when you're ready.
Hello, David. Thank you so much for a very interesting presentation. My name is Phil Kim. I'm a program director at ARPA-E. Yeah, I have a question about if there's any increase in pumping cost or energy when you are using this solid particle containing HTF, and how far can you pump in terms of, again, pumping cost in addition to the insulation cost? Therefore, do you think it's economical to connect distant heat sources to demand using this approach?
Yes, thank you for the question. You know, through the ARPA-E analysis, that was one of our milestones, is to look at the pumping capacity and the amount, percentage of pumping parasitic loss that would be encountered. And what I would say is through our systems in the laboratory, we were well below our milestone criteria. And even for scaling a system at 2 megawatt size capacity, which was one of our milestones as well, our milestone goal was to be below 5% loss in terms of parasitic energy there. And we were better than half of that. We were right around 2%. So I do think it's possible. We had very low pumping loss through our systems during the test campaigns. We've done a lot of extensive testing at GTI in the particle work, and the calculations show that as we scale it up, that the parasitic loss would be low as well.
Thank you. Yeah, it sounds like this is almost like a power cable for thermal energy.
Yes, yes, exactly. Just imagine, you know, in the old days, you have those, you know, cables that you hook up, and this is certainly a conduit for thermal heat.
Yeah, thank you so much.
Great, thank you for your question. I also see there's a Paulette Gregorian that would like to ask a question. Paulette, I'm going to go ahead and unmute you. You can speak now, Paulette.
Okay. Thank you, Alan, and thank you, David, for this wonderful presentation. I have two questions. The first one is, if we are not to store the particles and send it directly to the process line, are there any limitations as far as the type of heat exchangers that are going to be used?
Well, when you're flowing particles of this nature, there's a couple criteria that you really want to be aware of. You want to have long radius elbows, and you don't want to have a lot of multiple passes. We're studying the heat exchanger aspect in the laboratory at GTI, and we're also looking at the flow through various types of heat exchangers. And we realized that not all applications would want to store the particles. They would want to send it directly to the process, and then would have a bypass as well. So as long as you take into account those type of pumping and piping arrangements, the particles will flow freely through the system.
Okay, thank you. And my second question was that has there been a study as for how long are these particles capable of holding the temperature, like the concept of temperature versus time?
Yes, that's one thing that we did not perform a calculation on. Once you have a hopper full of hot particles, that hopper would essentially be insulated to the surroundings. I think it would just be a standard heat transfer calculation that could easily be accomplished. In the earlier work, though, we looked at transporting the particles through the system, and we did perform tests that equated to, on the smaller test rig, about 11 years of operation. And we found that there was no degradation of the particle, meaning no breakdown of the particle. We did a particle size analysis of the particles before and after the test program, and also did scanning electron microscopy of the particles itself with no detrimental effects. So I think it would be easy to calculate the heat transfer loss and how long those particles would hold temperature for it.
Okay, thank you. So technically it's better if they are directly sent to a process rather than a storage.
No, I wouldn't say better. I would say it really suits what's better for the application. There may be applications where it would be advantageous to store, but in terms of free flow of particles through the process, it could be consumed as it's generated as well.
I see. Perfect. Thank you.
You're welcome.
Thank you for your question. I did receive another written question from Kevin Duell. His question is, are there any pilots in play for direct industrial use?
Hi, Kevin. Interesting question. The only, well, we're moving towards a demonstration in Southern California that I alluded to earlier. And then there's also a demonstration at GTI that if I'm fortunate enough to see you next month, I may be able to show you in person.
Great, thank you for that question. I see that Jesse Martinez is raising his hand. Jesse, I'm going to go ahead and unmute you so that you can speak.
Thank you, Alan. Very nice to meet you, David. My question is twofold. I saw that you did post some, financial information about the particle itself, and I think I saw that the cost is in the $23 range. Is that correct?
It was $16 for the particle, 23 for the molten salt.
Okay, so thank you. So it sounds like it's a performer economically, and by economies of scale, is there an idealized application for the high temperature range, specifically, tending in towards the 1200 degree F or the 650 C? Specifically looking at idealized duty for heat exchangers and mass flow rate of the media that's transferring.
Yeah, I mean, there's a couple things that come into play there. If you separate out and you're not focused on the power block, it certainly makes it more easier and more economical, and because the power blocks are quite expensive. I would also say that there's a distinct threshold when you start to approach the 600 to 650 degrees C temperature regime in terms of available valving. High temperature valves become much more costly once you go over that temperature point. So I would think in terms of process application, those are parameters that would need to be taken into account as well. So on the surface, I would say that there would be greater economics if you were to be somewhere between, say, 500 to 600 degrees C, because you wouldn't necessarily have to deal with those higher temperature material issues.
I appreciate that. Thank you.
Thank you for the question.
Great. I don't see any other questions. I do want to give an opportunity for people to continue to ask questions, so I'll go ahead and throw out a question of my own. So Dave, given that this is a rather early stage technology being supported through ARPA-E, what do you foresee the future work would be for something like this? It seems like it has a really wide application, and that's pretty exciting. And there's definitely a need for this type of technology, and also that it can achieve process heat that's much higher than what's on the market today. So when do you think it will be able to commercialize something like this?
Well, we're trying to move towards the commercialization path presently. We're working with Stanley Consultants to put together a solid engineering package that could be used by, engineering firms to spec it out. And the ARPA-E Summit is coming up in May, and we're hoping to be able to host a panel discussion at the summit and attract those entities that may move the technology forward for commercialization. The GTI is a not-for-profit organization, so we don't manufacture any technology moving forward, but we're looking for those partners that would be able to build and service and represent a technology like this in market. And we've had several discussions along. We have a couple interested parties, and we hope to be able to, start having closure on that topic more than likely in the second and third quarter of this year.
I see. Thank you for that. I don't see any other questions, and I do want to give an opportunity for the audience to continue to ask questions. Does anyone have any other questions that they'd like to ask Dave? before we leave? Well, I don't see any other questions for today, and it looks like we're just about time. So Dave, I'd just like to thank you today for today's exciting presentation. We do look forward to the results of your research and what would come next from it. And just as a reminder, this webinar is being recorded and will be available on the SoCalGas Research and Development website. Thank you everyone for your attendance today. Take care and stay safe. Goodbye.